it, but every time you need to detect whether there is deadlock or not. Avoidance is for each step you need to check whether there exists the chance to enter the deadlock. Okay? What is the last solution? Ignore. Okay. Yes, that's the most popular way. Because all of this, the process, deadlock solution is very, very expensive. Like the graph theory. Because it's based on the graph theory usually NP complete. Then, what is NP complete?
The time complexity of the algorithm is not polynomial.
Yes. In other words, there is no optimal solution, only brute force way. So when you have the n number of node, n number of process, it will be n squared. Okay? That is it's not n squared, it's n to the power of n, actually, or n factorial. There is no optimal solution, non-polynomial answer at the computation. So it's very expensive. So most of operating system or system allow the deadlock. In case the deadlock, each processor will be in charge of. So that's the reason sometimes you operating system is a hand, so you control C and kill the process using the task. What is the name of that? Task manager, right? So that is a deadlock. So based on that idea, we are going to resolve that problem. Conflict is kind of a locking problem, deadlock situation. So how can we resolve? This is waiting each other. How can we solve the problem? First, wait die is, there is just the two process. One is I, another one is J. TS means timestamp, the time when the transaction is started. In this case, which one is older? TI is the older one. Start first, then start next, right? The timestamp is the lower than TJ. That means this is older, this is the first one, then this is the second one. Then if that it has the conflict, one of them should be die here. Yes. Which one? In this case, so T1 is to wait and the TJ will be the younger. Older is waiting, the younger will be die. Okay? That's the user, I don't know. But that anyway, that is wait or die. Who is waiting? The older. The first one is waiting and another process transaction will be die. Die means aborted. Falsely terminated in database. Okay? Another way is wound wait. Wound wait is a little bit. It's not exactly the opposite way. Little bit opposite. It's similar to the opposite. So in case the conflict situation is a locking problem, then so if the TI is younger than TJ, which means either older than TJ is the first one, the second one, and abort this one.
Right? It means wait to die. If TS means one starts 5:45, another TS TJ it starts means 5:50. Means 5:50 is means older, and TI is younger means 4:45. In case means TI started before, so TI to wait because it already has done means finish 5 minutes before that one. So in that case, TI is allowed to wait.
I little bit missed the one point. So, for example, there exists the TI, then the TJ is the younger one, is the later transaction. So TJ, if the TJ cause the conflict problem because the TJ requests the same item, at that time, in this case, TI is older because TI is already acquired the lock. Then TJ requests the lock. At that time, TI has the responsibility of that. So still waiting. Okay, still have the lock. However, if the TI is younger, okay, TI is actually started later, but got the request the lock first on data item X. Then, because TI is younger, then we do better kill. That terminate the process. Otherwise, if we allow even TI younger transaction, later transaction wait, it's just keep waiting. One of them should be die and another item can wait. Only one item. At that time, who will wait? If the first request, TI request first.
Yes.
Then this is the older one. The first started first. Then still have the chance to wait the data item. Then later TJ will get the chance. Okay? Otherwise, so if the TI already request, then TJ the request the same item. However, TI is younger. It's started later. You don't have a chance to wait because only one of them will wait. In this case, it's a serial. TI started first and request first. So if that is done, then TJ will get the lock. However, if TJ the request first, TI request first, then TJ request. However, TI started later. Okay, then it's forever. It can be forever waiting. Not always, but it may have the chance of the deadlock. So that is the wait or die. Okay. However, wound and wait is a little bit different. So TI started first and TJ the next. Then TI request and the followed by the TJ next. Then at this time, we firstly terminate the later younger one. Okay. Then clearly we solve the problem. If the TI is younger, which means TJ is the started first, then it's a little bit opposite way. So TI is allowed to wait. Younger is the newer process still have a chance. Which one is popular? Wait die algorithm is more popular because it's easy to understand. First one is older. If the transaction started first, still have a chance. Because I started the first and request the data item earlier, so I still have the chance. If the order is opposite, we will kill that the process terminate to avoid such a deadlock situation. When for the strict case, strict two-phase locking. Okay, so this is the most popularly used two-phase locking algorithm. I'm going to skip this part. The deadlock and starvation is a general. Then let me show you one of the example of that. Okay. So we are going to implement a wait die algorithm. This is an example of the locking manager. This is a transaction list. So we have, in this case, 3 transactions, 1, 2, 3, and it has a B stands for the beginning, and E stands for the end. And so, for example, first, the beginning transaction 1, and transaction 1 read the data item Y, and write the data item Y, and read the data item Z, and begins the transaction 3, and so on. So this is the transaction table, this is the lock table. Both of them are managed by the lock manager. Okay, so for example, when the transaction 1 started, we will update the T1 is started. So we will update the transaction table. It's active or the disabled. So there's no lock information. So then, next, transaction 1 try to read the data item Y. To read the data item Y, transaction 1 need to get the log from log manager. So this is the can see this one. So, for example, read log on Y by transaction 1. So, log table will be updated like the data item Y is a read log and shared log transaction ID 1. Then you can easily see the current status of this system. Only data item Y is logged by the transaction 1, which is the shared log. Okay? The next, transaction 1 try to write the data. Okay? That is the write log. It's a upgrade the log. It's a promote the log. Okay? Then read the data item Z. To read the data item Z, you need to get the log. Okay? So far there's no problem. And then start another transaction. Transaction 3 is active. And also you need to keep the data item owned by, shared, locked by the transaction, and so on. And transaction 3 would like to read the data item Z, Y. But Y is already locked by transaction 1. It's a conflict. That may cause the deadlock situation. That may cause the concurrency problem. So we need to resolve that problem. How? Using wait-I algorithm. So in this case, transaction 3 is younger than transaction 1, which means T1 is the first and then T3. And T1 already got the log. Okay? Then it's a responsibility on that data item, which means the younger one should be die. Otherwise, if T1 requests something item owned by T3, it will be deadlock. Deadlock prevention, deadlock avoidance, deadlock
Starvation.
whatever, detection. It's not always the deadlock. That may cause the deadlock chance. So this one is also, if you allow the both request, transaction 3, acquire the lock on Y, if you allow it, it may cause the deadlock. Okay, later. So we need to address that problem using the wait-I algorithm. So younger one, this one is younger one, will be die. So abortive. All the other operation request by this transaction abortive. Then transaction 1 write the data item Z is the upgrade. There's no problem. And E1 and transaction 1, which means commit. Then end of transaction. So there's nothing on log table. And we start the transaction 2 read log. It's okay. And it's upgrade. And transaction 3 request is already terminated, right? Transaction 3 is already terminated, so aborted. And it's already aborted. Transaction 2, yes, you can get the read log and write log, then end. Then we will not get any chance to enter deadlock situation. We can provide the concurrency of the data to all the user. I know this may not cause the deadlock situation even though we do not abort this one, but it may have the chance to enter deadlock situation. That's the reason we apply the wait-I algorithm not to enter deadlock situation. In other words, to provide the concurrency control to all the transactions. So that is the concurrency control in database. Who is in charge of that? Log manager. In other words, this several times I offer the project to implement the log manager. You can just implement this one, and that's it. Not very complicated. Okay? So I don't think I upload this file. I will upload today, tonight, or tomorrow. Okay?